Alrighty, y'all. Well, I just you two today. Maybe someone else will show up. But hi, welcome. Do y'all have any questions that you want to specifically see? Or anything? Just want to go over a couple like practice problems from stuff we've done this week. Okay, great. Okay. Like formal charge and stuff, is that what we're mostly working?
Kind of stuff like that.
Yeah.
Like drawing those structures.
Yeah, absolutely. Okay. Do we feel comfortable with like the steps for a Lewis structure, or we just need some practice with them?
We can do it. I'm not-
Okay. Yeah, absolutely. Absolutely. Alrighty, so let's start off with let's do where's like carbon tetrachloride. We'll start off with CCl4. And we want to draw the Lewis structure for this. Okay. So the first thing that we're going to do when we're drawing a Lewis structure is what? We want to count our valence electrons. So for carbon, do we know how many valence electrons that has? 4. And then what about chlorine? 7. Yep. And we have 4 of those. So we have 4 plus 28. So we have a total of 32 electrons. What do we do next? We're going to draw a skeletal. So what goes in the center? Carbon's going to go in the center here. And how many bonds is carbon going to make? It's going to make 4. And then chlorine will go on the outside of all of those. We had 32 electrons and we just made 4 bonds. So how many electrons did we use with those 4 bonds? Perfect. So how many remain? 24 remain. And where did those 24 go? To the terminal, and those go as lone pairs to our chlorines. This should be 6 on each of our chlorines because they get 2 from that bonding and its octet, and then 6 non-bonding creates an octet of 8. How many electrons did we use there? That was 24. Do we have anything left over? Nope. And if we check all of our octets, or if we check the octets of all of our atoms, are they all happy? Do all of them satisfy the octet rule? Yep, so we don't need to draw any double bonds or anything, right? We can just keep it as is. Okay, does that make sense for drawing a Lewis structure? We can calculate the formal charge while we're here, just so that we talk about it. Do you remember what the formal charge formula is? Okay, it's totally fine. So that's going to be the number of valence electrons minus the non-bonding electrons minus 1/2 bonding electrons. So what we mean by non-bonding, that's going to be any of our lone pairs. So any of the dots that you see here are going to just count that directly. And then the half the bonding electrons, that's going to be from any of the lines that you draw. So right, if you have a double bond, usually 4 electrons are in that double bond, but we're saying, okay, we're going to split those equally. So this atom gets 2 and this atom gets 2. That's why we take half. One very easy way to count this is by counting the number of dots you have and counting the number of lines you have. So in the case for the bottom chlorine, how many dots do we have? Yeah, we have 6 dots, and how many lines do we have for that chlorine? We have 1 line, right? That would be the same as if we said, okay, there's 6 non-bonding electrons, and then half of the 2 from the bonding is 1, right? So you can just count your dots and lines. That works for double, triple, anything like that. Okay, so if we wanted to find any questions on the formal charge, what that means? So if we wanted to find the formal charge of carbon, how many valence electrons does carbon have? Normally from the periodic table. 4. Right, that's always going to be, when we say valence electrons, that's what we mean from the periodic table. Does chlorine have, or not chlorine, does carbon have any non-bonding electrons? Nope, so we have 0. And how many lines, or 1/2 of the bonding electrons? How many is that? All right, so we end up with 4. We have 4 lines, which is 8 total bonding electrons, and we're going to take 1/2 of that, right? So 1/2 of 8 bonding electrons is equal to 4. And so that gets plugged in here. So our formal charge of carbon is going to be what? It'll be 0, perfect. Do we like formal charges of 0? Yes. Okay, so if it has a formal charge of 0, then we're just going to keep it as is. We don't need to like indicate that it's a formal charge of 0 on our structure. We could do the same thing for the chlorine, and all of our chlorines look the same here. So if you find the formal charge of 1 chlorine, it's going to apply to all of the other ones in our system. So for the formal charge of chlorine, how many valence electrons does chlorine have usually? 7. How many non-bonding electrons does it have? It has 6. How many bonding electrons does it have? 2, but we're going to take 1/2 of that. So we say 1/2 times 2. So we end up with 7 minus 6 minus 1. So what's our formal charge of chlorine? Also 0. Right, so this is also good, right? Since all of our atoms have a formal charge of 0, then we can say that this is happy. This is going to be our best Lewis structure for our system. Okay, does that help with both of those? Just want to do a couple more practice problems like that? Cool.
Yeah, let's try these.
Okay, so we have H2S, SO3, NH4 plus, and PO3 3 minus. I'll give you a couple minutes to work on them. Take your time. Ask questions when you have them. How are we doing on these? Good? Is there one that we're stuck on or we finish? Big silence is a good thing. Okay. All right, so I guess we can go over them. So we'll start with number one. We have H2S. How did you draw that? Anything else? Awesome. Yep, so we should have something that looks like this. So this looks very similar to if we were to draw H2O, right? H2O. We said also looks like this. Oxygen and sulfur are right underneath each other on the periodic table, so they will have very similar structures when you switch out like hydrogen or something, when you pair them with hydrogen or anything like that. Because they both have 6 valence electrons, and then your hydrogens have 2. So that's fun there. Started briefly talking about like electron domains. How many electron domains are in H2S? Yep, and where do those come from? Awesome. Right. The bonds in the lone pairs are each their own domain. So we have 2 bonding electron domains and we have 2 non-bonding electron domains. So we have 4 total electron domains. Does anyone remember what the shape of that is? This will be your tetrahedral. You'll get a lot of practice using that one. Okay, any questions on H2S? Awesome. What about SO3? How did we draw this one? What element's in the center? Sulfur's in the center. Or I guess how many, before we even start drawing that, how many valence electrons should we have with this one? We should have 24 total electrons. So we have S in the center. How many bonds is sulfur making? 3. With oxygens on the outside. What goes around those oxygens? Is this our best Lewis structure? What's wrong with it? Right now, this does not have a full octet. So how do we make that happen? Awesome, right? You can take any one that you want, make it a double bond. So we end up with sulfur trioxide with 1 double bond. So what structure, or what does this structure have? Or I guess, is there an alternate structure that we could draw for this one? Good, so this one has resonance structures. How many other resonance structures can we draw? 2 other ones, right? What could we draw? Awesome, right? We can change the double bond so that it's on the left-hand side. Or we can change the double bond so that it's on the right-hand side. So we have 3 total resonance structures between the 2 of them. What would we expect our length to be for the bonds of all of these? So I guess, do we expect to see a double bond? What do we have to do if we have resonance structures? Do we look at them each individually? So whenever we have resonance structures, we always want to make sure that we're looking at a combo or an average of all of them. So we're actually going to see a structure, right, that has these partial bonds in between all of them. So they're not actually double bond character, they're not actually single bond character. What are they gonna be about? How many total bonds do we have from sulfur to oxygen? We have 4, right? We have 2 single bonds and then 1 double bond. So we have 4 total bonds. How many positions can we put the double bond in? There's 3, so we can divide that by 3. So we end up getting that the bond length is about 1.33, right? So it's a little bit shorter than a single bond, but a little bit longer than a double bond. Does that make sense how we found what the bond would look like and actually look like? That makes sense, taking the combo of all of them? I can show you another example with resonance after we finish these other 2. Are there other questions on SO3? Does that make sense? How about NH4 plus? What does that one look like? How many valence electrons do we have here? This is just 8. Right, we have 4 from our hydrogen, and then usually nitrogen has 5, but we have a plus in our ion here. So we're going to take away one of those electrons. So we only have 8 that we're working with. What goes in the center? Nitrogen. How many bonds does it make? Makes 4. And what about that plus? What does that plus indicate? Yep, so it's an ion, which means we need bracket notation, right? So we need to say that something has a plus next to it. That also means if we have a plus, that one or more of our atoms will have a formal charge associated with it. What would be the formal charge for nitrogen? How would we solve for that? Yep, and how many valence electrons does nitrogen usually have? Nitrogen usually has 5. How many lone pairs does it have? Has 0. How many bonding electrons does it have? Close. How many lines does it have? It has 4, and how many electrons are in each of them? 2. So we have 8 total and we take half of that. Yep. So we have 1/2 of 8. So the formal charge of nitrogen is 5 minus 4, which is 1. Right, so nitrogen here has that +1 charge of for its formal charge. This is still our best structure for NH4+, because at some point we need to have something with a positive charge, because our overall ion has a positive charge. Right, if we have a negative charge, that means that something needs to have a negative charge, because our overall ion has a negative charge. So we can draw that too, or we can figure that out too. So what, for this formal charge, how many valence electrons does hydrogen have? 1. How many lone pairs does it have? 0. How many bonding electrons does it have? 2, so 1, right? We're gonna take 1/2.
So they're all 0.
Yep.
That's why the charge on this one.
Yep.
Okay.
So the formal charge of all of our hydrogens here are gonna be 0, which is good because we want to minimize formal charge for our structure. So the only thing that we can have, we only have one atom with a formal charge. And so that's minimizing it to the best of our ability for our Lewis structure. Questions there with formal charge on NH4+. Does that make sense for this one? Right, so how many electron domains are in this NH4+? Also for us, what was that shape? Tetrahedral, awesome, right? So we have 4 electron domains, which is tetrahedral. Great. Going back to SO3, how many electrons domains were in SO3? So just look at one structure. How many electron domains are there?
We don't count the lone pairs on the other atoms?
Right. You're just doing your structure for, or you're just doing your electron domain for this central atom. Yep. So there's 3. Yep. And that comes from, right, single, single, double, if you're looking at the broken up resonance structures, right? But we know it's gonna be 1, 2, 3 for this one. Okay, so this one, does anyone remember what 3 electron domains? Yeah. Yep, trigonal, planar.
So we just,
Yep, yes, yep, your electron domains for your terminal atoms don't really matter too much. If we have something where it's like CH3OH is methanol, that's a big one. It'll end up looking like this. In this case, we have 2 central atoms. We have the carbon and we have the oxygen. So in that case, you can have a structure for the carbon and you can have a structure for the oxygen. In both of these cases, they both have 4 electron domains, but you'll get more practice with that later on. All right, any other questions on NH4+? And then what about PO3, 3-? How many total electrons do we have here? Yep. And that came from 18 from our oxygens Phosphorus usually has 5, and then we have 3 additional ones. So 26 total. What goes in the center? Phosphorus goes in the center. Well, how many bonds does it make? Makes 3. Where do those go first? On the oxygens. How many did we use with our lone pairs? 18. How many are left? There's 2 left, and where do those go? On phosphorus. Awesome. What's our formal charge of the oxygens here? It is. How do you get that? Mm-hmm.
6,
Perfect.
then you subtract. Also 6.
Mm-hmm.
Have
Yep. Perfect. Right. So your formal charge of oxygen is -1. Is that the same for all of the oxygens in this structure? Yes, right. So all these have -1s next to them. So what's our total formal charge for PO3, 3 minus? It's -3, right? Because we found the formal charge for phosphorus. This is 5 minus 2 minus 1/2 times 3, which is 0. So since phosphorus has no charge and our oxygens have a -1 charge, that adds up to -3. We have a -3 in our ion to originally begin with. So all of our formal charges need to add up to that -3. And it does, so that's good to go. Yes. Yep, so it kind of depends on how you want to show it. You can either show the -1s like in the charge thing next to it, or you could put it in the bracket notation and say -3.
When we say lone pairs,
Mhm.
that's
2. Yep,
but in the formula, it's like electrons in general.
yes.
That's why that middle number is 6 and not 3.
Yes.
It's not.
Yep.
Oh.
Yep, because it's your number of non-bonding electrons, so they specify that as, right, like individually electrons. That's because sometimes like nitrogen will have a radical on it, right? So that's a 1 for it. So that's why I always like to think of it as the dots minus the lines. Because you can just count how many dots and lines it has. Okay. Is there something else I wanted to talk? Yes. So you could have said, right, oh, that has a -1 charge. Maybe I can draw a resonance structure for PO3. So we could say P, make this one the we'll make this one the double bond on the left-hand side. If we drew this resonance structure for it, we can see that the formal charge for the 2 oxygens on the bottom and on the right are going to be -1 still. But what is the formal charge of the double bonded oxygen now? It's 0, right? So we have 4 and then we have 2, so this is gonna be 0. What's the formal charge of your phosphorus? Supposed to have 5 valence electrons. How many non-bonding electrons does it have? 2.
Sorry.
Yep. Right, so we end up with phosphorus having that -1 charge now. So it still adds up 2 minus 3, but what's wrong with this structure here? Why is this not the best structure?
It's like all that way.
Nope.
Trace.
That's still okay. If something's gonna be negative, does that mean that it has more or less electrons? It has more electrons. So when we're looking at formal charge and where to place that negative value, we want to know, okay, which one's more electronegative? What's more electronegative, the oxygen or the phosphorus? Oxygen's more electronegative because it goes fluorine, oxygen, nitrogen, carbon, and then phosphorus is down here. So it's a little bit farther away from fluorine than oxygen is. So since oxygen has 0 and phosphorus has -1, this is not following that rule where the more electronegative atom needs to have that negative charge. So that's why this top structure is better than the bottom structure. Do we see that, why it's
That also apply to if the overall charge was positive.
yes. Yep, we still want that positive one to be on the least electronegative. Yep. And the only one that will not have a formal charge is hydrogen. So, right, for like NH4 plus, the hydrogen can't have a formal charge usually, so that's why the nitrogen gets it. Any questions on resonance structures, formal charge, Lewis structures? Does that help? Yeah, okay. And then we talked about one example in class. It was ClO3 minus. And if you remember, we made it so that it looked like this. So our oxygen on the right here in this case is the one that has the negative charge to match our ion. In this case, how many other resonance structures can we draw with this structure here? Right, we are always going to have 2 double bonds and 1 single bond. How many other structures can we draw? It'd be 2 other ones, right? So we would have 3 total. Right, so that -1 charge gets moved around to, right, the various oxygen molecules. But now we know that these are resonance structures, so we know that the actual thing that we're going to see is a combination of all of these. So looking at just one structure, how many bonds are being made to the chlorine? There's 5, right? So we have 5 total bonds. How many different possibilities are there for that, I guess now, single bond to be? Right, so how many different locations can the single bond go? There's 3, right? Because we drew 3 different structures. So what's the characteristic of the actual structure or the actual bond length for our ClO3, for our ClO bonds? 5 divided by 3, so we have 1.67. So is that going to be longer or shorter than the double bonds? So if we were just saying I have a single bond and a double bond, is it going to be closer to the single bond or is it going to be closer to the double bond?
But like, what is the length of a bond?
That's like that's a given. It depends on it'll change depending on the double bond and on the atoms associated with it. So like, but if we're looking at, we'll just say like the chlorine ClO on the left. Even if I gave you this was 10 and this was 3, right? Those were the lengths of them. Where do you think the 1.67 bond length would be closer to your double bond side or your single bond side? It'd be closer to double, right? Because if we're looking at a number line, we have a single bond and we have a double bond. Right in the center is 1.5. But we're over here in that 1.67 area. So it's going to be closer to that double bond characteristic than that single bond characteristic. Which is different from the other one we talked about, right? That had a 1.33 bond characteristics. That was over here, right? In 1.33. So I had a little closer to a single bond. Does that make sense in terms of like the averaging and everything? Are there any other questions on?
I don't know, but like when you're counting the domains, you do count in pairs, right? Not in.
Right, yep, when you're counting the domains, it's in pairs. So how many domains do we have for the ClO3? Yep, we have 4. We'll have this one, this one, this one, this one. This one also is a tetrahedral. I feel like tetrahedrals are very common, so. And it doesn't matter if it's double or single or triple bond, all those count as one electron domain, right? One tether of where something is being bonded. Alrighty, any more questions? Any more practice you want to see? The chlorine, there's 4. Because we have 1 for each of the chlorine oxygen bonds, whether it's double or single bond. And then we have a lone pair for all of them as well. I don't know if that's, might not be able to see that. There's a lone pair on all of these.
Oh, I see.
Sorry,
Sorry.
kind of gets washed out. Mhm.
In another scenario, what would be the, I guess, kind of formula for that? So it's like total bonds
Over like possible positions, I guess is a good way to put it.
of the
So it's gonna depend on what's like different from the rest of them. Yep. All right, so when we looked at the SO3 minus, or the SO3 earlier, right, we had one double bond and then two single bonds. And so in that case, the different bond was the double bond. So how many different possibilities can we have for that double bond? That's like the odd man out. But in the ClO3 minus, the odd man out is the single bond. And so that's like, okay, how many different possibilities can we put that single bond?
And that was the 1.67. Was it, the length? The estimated length,
Mhm.
like all the bonds?
Yes, yep, because we're saying that each of the Cl and O bonds between this atom here, it's not gonna be, oh, one has a double bond length and one has a single bond length. They all will have a 1.67 bond length.
So that, like, final one is combination.
Is a combination, yep, an average of all of them, yep. All right, and what has more energy, a double bond or a single bond? A double bond has more energy, right? So if we have this 1.67 bond length, that's saying that it's acting like a 1.67 bond. So it's going to require less energy to break than if it were a double bond. Thank you. Does that help answer your question?
We would still draw it in one of those forms.
Yeah,
We would just know that that's what the length.
yes, yep. I don't think that you'll ever have to be required to draw like an actual resonance structure. You would have to draw the resonance structures and not the overall one. Yep, you would like say, okay, this is a possibility. I see that I could have resonance. Here are the other options that I have. Or be able to at least identify ones with resonance. Yep. Yeah. Any other questions that we might have? Mm-hmm.
Is it the overall, what is it, the overall? Not the individual.
Oh, the dipoles and everything?
The
Yes.
overall dipole.
The overall dipole, yeah, absolutely. Okay, so did you already do lab? Yes, you know about dipoles. Okay, so let's look at the chlorine one again while we're here. So we have, I'll just draw one structure. Okay, so knowing the shape of your molecule is what's really going to help that overall dipole. So when we draw a dipole, this is going to be for right, the individual bonds that we have. So what is more electronegative, the oxygen or the chlorine? The oxygen is more electronegative. So your dipoles are all going to pull out away from that chlorine molecule. So it'll point this way, and this way, right? It's thinking about, right, you have a dog on a leash and you're trying to pull your dog along. So you have more tug going towards the oxygens. But the problem here when we're drawing, so it looks like, right, if we were going to pull on both sides and then pull down, it looks like our overall dipole would be going down the way that we drew it. But this is where your shapes come into play, because how many electron domains did we say this one had? This had 4. So what's our shape? Tetrahedral. So instead of your directions being pulled to the side and down, we actually have it where it's like the tripod, right? And we have the lone pair sitting up top. So they're all pulling this way. They're pulling out and around in a three-dimensional way. They're not just pulling straight down. So in this case, your dipole is, your overall dipole is still going to go down, but that's because of the lone pair at the top of your tetrahedral. It's saying, okay, this has a lone pair here, and I have my three dipoles pulling in each direction. So overall, if I pull in the same direction going down, it's going to be an overall dipole going down. Does that make sense why that looks like that? A good one to look at this is CH2Cl2. If you look at it this way, carbon's going to make 4 bonds. 2 to hydrogen and 2 to chlorine. If we want to draw the dipoles for each of these, which way are they going to go? We'll say those are neutral, right? Doesn't really matter about those. The chlorine ones. So the chlorine is actually going to be a little bit more electronegative than the carbon. So they're going to point outwards. So in this case, where's our overall dipole pointing? Or do we have one? The way I drew it makes it look like no, right? But how many electron domains do we have? We have 4, which makes it tetrahedral. So if we're going to look at it, right, we have the 3 on the bottom, and then we have the 1 up top. So that might be that my pointer finger is going to be the chlorine, and then the 1 up top is the other chlorine. So now they're pulling this way. And which way does my molecule go? Right, it goes pulling up and also pointing with my pointer finger, because these two are hydrogens, right? And that doesn't matter. It's not actually symmetrical because it's a tetrahedral and 3-dimensional. Do we see that a little bit? Right, so we're actually going to pull this way. I don't know if I have something in here that I can like show with, other than my fingers. Right, or even if I show you, right, these are the tripods, right? And then this is the hydrogen up top. If these two are my chlorines, I'm going to pull on this side and pull on this side. So they're going to go down this way. It's going to go straight down because the hydrogen's not doing anything in the back and the hydrogen's not doing anything up top. But these two chlorines are pulling the dipole. And so the overall dipole is going to be down.
And the other way you said that was because it's not directly under it, right? Like
Yes.
It's not, was it axial?
Yeah, it's not axial. Yep.
It's like crooked.
Yep, it's
So it
crooked.
can't, like,
Yep, it's 3-dimensional, so it can't cancel each other out, right? The way I drew it here, it looks like it's all 90 degrees, but it's not 90 degrees. It's 109 degrees between all of them. Because it's actually a 3-dimensional object.
Does that mean that we can also go this way or no, because of the how hydrogen?
Yeah, it depends on how like it's oriented, right? So I said if this is my chlorine and this is my chlorine, then it's gonna go this way. But if these are my chlorines, it's gonna go this way. If these are my chlorines, it's gonna go this way, right? It all depends on how it's oriented into space for it to move where the dipole is.
And how would we know to like what the correct orientation desired is? Or would it be based on how we draw it?
It'll just be based on how you draw it. So, as long as you, or maybe they'll give you a structure and they want you, based off of how they drew it, draw in the overall dipole. And if that's the case, then you just go off of the structure that they drew. Yep. Does that help a little bit? Once you get more into the shapes, it'll be a little bit easier to like see that too. With a little bit more practice. Do you have any other questions?
I do have a question
Yeah.
about, finding polarity when it's like compounds, like long compounds.
Mhm.
How do you decide the overall polarity as well as like these, well, this one kind of made more sense with the, like with the pool. I think how you rate it here made more sense, but just when it's a lot more.
Yes,
like,
so-
how do you distinguish the single relationships?
So when it's like. Like this guy here, yep. So you're just gonna break it up like bit by bit, right? You're gonna say, okay, what's my central atom with the carbon, right? How do those four elements around that play into my dipole? And they're gonna look at oxygen and say, okay, how do those? Oops. How do those play, right? So we're gonna break it up into two things. We're gonna say, okay, this is gonna be what I'm gonna look at first, this carbon as my central element. So is there any polarity difference between carbon and hydrogen?
Yes. Polarity.
Right, is there electronegativity difference? Or do we count those as the same?
I would think that there is, but.
Yeah, you would think that there is a little bit, but it's so small that we're gonna say it's non-polar. Okay, so anytime you see a carbon-hydrogen bond, that's gonna be a non-polar bond.
Is that because of their proximity?
Yep, it's because of their
Oh,
proximity
maybe
in
they're
like,
that close to oh, okay,
Yes.
yeah, I'm thinking myself, do we have to like, no, we don't have to memorize.
nope,
everything.
you just need to know the trend for it. And then if you know that carbon-hydrogen is a non-polar bond, then that kind of solves you for anything else.
And
you might
that
do.
is, that's where fluorine is for, that's the.
Mhm,
that
yes,
is-
yep.
And then so it increases as you go up in this way.
Yes, yes,
So these are like hydrogens like right here, and carbons are here.
Yep.
The difference is too small.
yep.
Non-polar, that's less than 0.4 or equal to.
Yeah, I think carbon has like a 2.4 and hydrogen has a 2.1, so that 0.3 difference is
That makes
essentially
sense.
non-polar. Yep. Okay, so we know that there's no dipoles for the carbons to hydrogen bonds, but what about the carbon oxygen? Is there a dipole there?
It's like most-
That one's more significant. Yep, so which one's more electronegative? Oxygen is, so which way are we gonna point our dipole here?
to the oxygen.
To the oxygen, yep. Perfect. Okay, and now we did that for the carbon. But we have another central atom for the oxygen, right? Because that's in the set, right? If we look at the whole big molecule, we have two in the center. So if you look at the oxygen as our central atom, we already called that the carbon to oxygen bond is going to be a polar bond.
Mhm.
What about oxygen to hydrogen? Is that going to be polar?
Yes.
Yes, it is. In which way is,
Far.
yep, in which way is it going to be? Inwards towards oxygen. Yep. Right, so both of them are pointing towards that oxygen. But are they pointing directly at each other?
Yeah, I mean, it looks linear.
It looks
But we
linear.
did evaluate it like in two different times.
Mhm.
It's not
And how many electron domains does oxygen have?
four.
It has 4, right? So it's actually going to be drawn like this. Where we look at it and the carbon, oxygen, hydrogen bond, right? The COH, that's going to be in its bent form, kind of like water, right? Where water, because of the two lone pairs. But if we look at the carbon that has its 3 hydrogens and then the oxygen, what shape is that going to be in?
Three hydrogens in the yard, tetrahedral.
That's also tetrahedral, right? But there's no lone pair, so it looks exactly like a tetrahedral. So instead of this hydrogen being on our bent water, it's actually just this CH3. So we still have now our dipole pointing this way and our dipole pointing this way. So what is our overall dipole going to be?
Can you say? Oh,
Yep, it'll be up. Does that help?
Yeah.
Yeah.
Initially, I was so lost.
Yep.
Oh my God.
Yeah, and like the more you play with your shapes, the more you'll see like, oh, this has 4, this is gonna look like this, and you can start drawing it in like that bench shape or planar shape, something like that.
And the last question I have.
Mhm.
It's just, let's say there were like 5 items laid.
Mhm.
Flat. You still pick central items because they have something on either side.
Yes, yep, as long as it has. Right, you're always looking at stuff like. We'll call it X, Y, X, right? If X is now bonded to another Y and then to a Z, right? How many central atoms would we have?
3.
We would have 3, right? We would have the Y, the X, and the Y, because we need to have it go 1, 2, 3, 1, 2, 3, right? As long as it ends on something, then it's a terminal atom, we don't care about it. But like this X could have a W next to it, right? This could have an H. This could have an H, this could have an H, this could have a lone pair, right? It just depends on what's around it, but as long as this W has nothing else next to it, and so that's gonna be a terminal atom.
And from getting it from the formula given to this form and
Mhm.
picking the central atoms.
Mhm.
Kind of, could you give like one example?
Yep, so I guess we could do like CH3OH. Right, we just did that one where the carbon and the oxygen were our central atoms. When it looks like this, we're saying, okay, this first one, carbon, is a central atom, and this oxygen is a central atom.
Only because the hydrogens can be central atoms?
Yes, in this case, yes. We could do something where it was, oh, this one had a good one. We had HCN, right? Which one's gonna be our central atom here? Carbon, right? Because hydrogen can't. Carbon's least electronegative compared to nitrogen. And then,
Would you draw that linearly?
yes, right, so you would draw it linear, you would say, okay, here's my hydrogen, here's my nitrogen. Right, and then you can go through your usual Lewis structures and try and find what the correct structure would be. Okay, does that help a bit?
Yeah.
Yeah.
That helps a lot.
Okay.
actually. Oh my God.
Okay, great.
Thank you so much.
Yeah, absolutely. Thanks for coming.
Here, then below.
And that's all.